Hello, students. This is Chapter 7's notes. We're going to introduce the planets and talk about how to get there, how to find stuff out about them up close. This image is Earth, a little tiny dot, as seen from Voyager 1, which was going around Jupiter and Saturn on their flybys. And we'll talk about what I meant when I said that. So, as you know, there are 4 terrestrial planets, 4 Jovian planets, 8 total. And then there's Pluto, whatever it happens to be. And it's grouped in with other things called dwarf planets. And then there's small bodies. That's what's in the solar system. And we're going to take some focus for the terrestrial planets. We're going to include the moon because it's a body that looks a lot like the other terrestrial planets, since it's a small rocky object, but it's fairly big. And when we talk about the Jovian planets, we're also going to talk about their moons because we can compare them to the terrestrial planets. And then we'll talk about the dwarf planets and the small bodies. And this is the thing is, it's fairly easy to just talk about a planet in and of itself, but by studying how they compare to each other, you can figure out processes that might apply to all planets or might apply to all planets of a certain type. So we're not just trying to figure out facts about the planets, we're trying to figure out information about how they formed, what they're doing now, that sort of stuff. All right, so of course we kind of have to start out with the sun. This is a tour of the solar system again. And so the sun is not a planet. Classically, in ancient Greek astronomy, the sun was a planet, in a sense. I mean, it was still a special thing, but, you know, almost all of the solar system is the sun, and almost all of that is hydrogen and helium. And it burns a massive amount of fuel, turning massive amounts of mass into energy. Going outwards is Mercury. Mercury is basically a massive cannonball. It is mostly metal and rock with a very large iron core, and it is heavily, heavily cratered with not much of an atmosphere, no water. It's a cratered cannonball. And it has extremes in temperature, very hot and very cold. Because there's no atmosphere, if the sun doesn't hit it, it's cold. If the sun hits it, it's hot. There's some more of Mercury. There's another one where this is enhanced so that you can see the different formations that show up on it. Okay, so Venus. Venus is kind of a cloud-covered thing. It has a very thick atmosphere, which makes the conditions horribly hot all the time. But otherwise, it's fairly like Earth. It's about the same size, probably the same makeup. It's just evolved differently. So here's visible light taken by a Galileo spacecraft, which went to Jupiter, but the way it got there was through going to Venus. And this is a radar map, which ignores the clouds and just looks at the ground features. And so you can see it's somewhat cratered, and there's some interesting geology going on. All right, so you guys know what Earth looks like. It's the only planet that we know of that's covered in water and in liquid water. And it's unusual in that it has a moon that is very big. The other 2 planets we've seen so far don't have moons, and all the other planets have very small moons. more of the Earth. Here is a very nice picture of the Earth at night, or at least a composite image where you basically see where the light is. And I think we've discussed this before. You can see certain features like the Nile and, uh, the North and South Korean border. And, you can compare various light sources here. And then here's a picture of the moon. So Mars is next. It's kind of Earth-like, but it's small. It has an atmosphere, but it's not that thick, and so it tends to be a colder place. But it has lots of geology, lots of volcanoes and canyons, ice caps, and we think it's also had flowing water at some point. And maybe it flows today in some limited areas, but it's a fairly dry place. Most of the water is frozen. So there's different images of Mars. There's visible, and then there's on the ground, because we've sent a bunch of robots there to look. So Jupiter, much farther out, much larger, and it's mostly hydrogen and helium. Has lots of moons. In this picture, what we're looking at in the near, on the right is Io, one of the moons, and we see eruptions from it. We see something coming off the surface. And then we see the thin ring that is around Jupiter. And, we see a few other things. There's several storms on the surface, including the Great Red Spot, which we'll talk about. There's more storms, more swirling in the atmosphere, and the banded structure that we see. And we'll focus in particular when we talk about the Jovian planets, we'll talk about the moons as well. And for Jupiter, it has the Galilean moons, which are the largest and the most active of Jupiter's moons. So Saturn is a little bit more subdued in other ways. It has storms and cloud bands, but they're fainter and lighter. It's a little smaller. It's also a giant and gaseous planet. And it also has a lot of moons. The two places where it has superlatives is the ring system that you can see here, which is massive and very highly detailed and structured. And it has a moon with a very thick atmosphere, Titan, which we'll study. And then so here's Uranus. So a lot of stuff has managed to get to Jupiter and Saturn. We've sent a lot of spacecraft there. To date, we've sent Voyager 2 to Uranus and Neptune. So most of what we know comes from that and from near-Earth observation. So ground-based telescopes and satellite telescopes. And so what we see here is a difference. Jupiter and Saturn were kind of orangish. Uranus and Neptune will be bluish. That's because Uranus and Neptune are both made of hydrogen and helium, but also of hydrogen compounds, which are things that will make ice. So water, ammonia, methane, that sort of stuff. And the methane in the atmospheres are going to make that blue color that we see. So Uranus is a pale greenish blue. Has moons, has rings, not too many of either. And let me go correctly. This is looking at it in a very unique way. If we look at Saturn, you can kind of deduce that the poles are at the bottom and the top based on the cloud bands. Jupiter is kind of weird. Based on the cloud bands, you can kind of tell this image is turned a bit. And if we go back to this one, you can see the same perspective. Okay. So Uranus rolls like a barrel. The poles are at the left and right, but we're oriented sort of correctly with respect to the plane of the planet's orbits. This is the way it orbits. Kind of unusual. Has an extreme tilt. Why does this keep going backwards? So Neptune, similar except for that axis tilt, has moons, has rings, has a little bit more structure in the atmosphere, some more storms and stuff. Deep, deep blue. Here we're seeing one moon, Triton, as we view here. And then we talk about the dwarf planets. We've sent something to Pluto to look, and for most of our understanding of Pluto, it was a lone planet, and then it was a planet with one moon. And now we see that it kind of has 5 different objects around it, at least 5 different objects. And what we see from these sort of things like Pluto tend to be much smaller, icy, and comet-like, which is kind of unusual. Now, that's not true of all dwarf planets. At least one is asteroid-like and just happens to be very, very big and planet-like as well. But there's a class of things that are basically giant comets that orbit around, and they fall in the class of dwarf planets, and we'll talk about those. And then there's comets. Comets have tails, have a bit of, like, we would probably call that an atmosphere, but it's not a permanent thing. It gets left behind. It forms the tail, which is gas escaping. And then we have asteroids, which are effectively potato-shaped rocks. Some of them can be unique. Some of them are solid objects, and some of them are piles of rock that have coalesced together. And so there's a lot of, your textbook has a lot of data of the planets, and the data is not a huge deal here. But what I'll point out is things we'll talk about in particular are things like the axis tilt, maybe the density, the surface temperature is going to be important. And what we notice is that stuff near the sun is hot, stuff away from the sun is colder, and stuff with atmospheres is warmer than stuff without. We'll talk about the composition. Terrestrial planets are rocks and metals. Jovian planets are hydrogen and helium and hydrogen compounds. And dwarf planets tend to be ices and rocks. And then there's the pattern of moons, which goes 0, 0, 1, 2, 67, 62, 27, 13, 5, 1. And for the things listed here is Jovian planets have lots of moons. Terrestrial planets tend to have no moons or very few moons. And we think Mars's moons are captured objects. They're not permanent moons in a sense. And so Earth is really weird for having this one big moon. So you've seen some patterns here. There's some other patterns. And in chapter 8, when we talk about the formation of the solar system, we kind of have to explain some of these patterns that show up. Right? Is the solar system has these patterns. We have to explain how they came around. And we'll talk about these features, but effectively, the planets all orbit in the same direction, and they orbit the way the sun rotates. And most of them also rotate that way. Venus doesn't, but it barely rotates at all. And Uranus doesn't, but it barrel rolls instead of rotates. So those two are weird. We're going to put that later. But most of the things orbit and rotate the same direction. There's the classifications between types. There's terrestrial and Jovian planets. The terrestrial ones are close to the sun, and Jovian ones are far away. And they're different types of planets. One's rocky and one's gaseous. There's lots and lots of smaller bodies. Where did they come from? And there are a few exceptions, right? We talked about Uranus's tilt and Venus's very slow rotation. And Earth has a really big moon. And we kind of have to explain how these things came about. So we have sent a lot of stuff into space trying to figure stuff out since we've been able to send stuff off the planet. I've given you a big list of stuff. I've tried to sort it a little bit. And these are kind of some of the more important landers and flybys and orbiters that we've sent up. Is that there's been other ones as well. Yeah, it is an abbreviated list, but I kind of hit the highlights of. All right, when we talk about Mars, we're going to talk about the rovers that we've sent there. When we talk about Pluto, we'll talk about New Horizons, which is the first mission out that way, which discovered a lot of new information about Pluto that we didn't know before, including pictures of something that actually look object-like instead of pixels on a screen. That literally some of the pictures of Pluto kind of looked pixelated. We'll talk about the missions to Saturn and Jupiter that have occurred, and we'll talk about some historical ones. There's orbiters of Mars and Mercury and landers on Mars, and the massive engineering feat of landing something on Venus and having it survive for over an hour. Right. There's a kind of an interesting thing. We land something on Mars and it will last years and years and years. We expect it to last 90 days. We land something on Venus and we're hopeful that it lasts an hour. And then the big two is going to be Voyager 1 and Voyager 2 because they told us a huge amount about the Jovian planets. And for Voyager 2, that's basically the only up-close info on Neptune and Uranus. And then, of course, there's Hubble and telescopes like it. So how do you get these things out there? And what do they do when they get out there? There's basically 4 types of missions that you can send a spacecraft on. And you have to do some trickery to get them to some destinations. And the goal throughout all of this is to spend as little energy as possible, which means that you're using the least amount of fuel, which means you have more space to send stuff. So you'll get missions that seem normally like a bit of a waste, like flybys. We send an object and it flies by and it never comes back. But by sending it once, we don't have to worry about burning fuel to do anything else. We can put more equipment on it to take measurements. So you get one shot at it, but you can put more stuff there and you can get to places you can't otherwise get to. Orbiters slow down and go into orbit around a planet. And that costs a little more energy to do that, but you get to spend a lot of time in orbit, which means you can do multiple measurements. Probes and landers land on the surface, and that costs energy because you have to slow down so you don't crash. And sample return missions bring stuff back, which costs energy because you have to take off from the planet. So these are sorted by energy cost or fuel cost. So flybys are send something once. It's cheap because you don't have to deal with the fuel. You don't have to deal with staying in orbit and taking data and dealing with the problems of sending the data back. But you don't have as much time either. This picture is the flight path of Voyager 2, which was very fortuitous. We launched toward Jupiter, and the gravity from Jupiter sent Voyager 2 to Saturn, and the gravity at Saturn slingshotted it to Uranus, which slingshotted it to Neptune. And the orientation of this was fortuitous, is that we launched in time to get to Jupiter in 79, and in 10 years later, we get to Neptune. So it's quite a long process. So orbiters orbit. You get more time, but you don't get to find out about the surface. You kind of have to do everything like satellite imagery. Landers let you get information on the surface, and there's a few different ways of trying that. We've tried, especially working with Mars's atmosphere, things like big airbags that expand around a craft, heat shields, parachutes, all sorts. And in the past, you just crashed, and crashing gave you some data. So we have probes and landers which land and explore the surface. And then most of what we've done for sample returns is send something to an asteroid or a comet, get a sample of it, and come back with it. Hayabusa is an example of that. Land on an asteroid, get some rock, bring it back. Of course, you have to design a spacecraft that can leave, which is more cost. And then one of the more famous sample returns is all the missions we sent to the moon. In this case, we didn't send robots, we sent people to get the samples. But effectively, the moon missions were sample return missions. And sometimes the spacecraft can have two parts, like Cassini and Huygens is an orbiter, Cassini, which orbited Saturn, and a lander, Huygens, which landed on Titan and gave us data about the goings-ons on the surface of Titan, which told us a lot about the surface geology. What we expect is liquid surfaces and weathering, as you expect, and an atmosphere. So a little bit more, how do we know the scale of the solar system? That's kind of an interesting thing. When we did Kepler's third law, at the very beginning, we talked about doing everything in units of years and astronomical units. And the reason for that is we didn't know the scale of the solar system. We had basically one measurement. We knew the Earth orbited on the Earth's orbit, and it took a year for it to do so. So we did all our measurements based on ratios with the Earth's orbit. Now, obviously, we don't have to do that. We can use Newton's version of Kepler's third law. But that means we actually have to know some of the details. We have to be able to measure the size of a planet's orbit. And the first way we did that is by very, very careful geometry. We looked at Venus as it orbited the sun, and on occasion, it crosses the sun's path. That's what's called a transit. The last one was in 2012. Venus won't do it again for another 160 years approximately, but Mercury will do it on cycles of something like 11 or 13 years. So in your lifetime, you'll get to see it again, a couple of times probably. But what happens is it's just a little dot that crosses the face of the sun, and you can time how long it takes to go across, and you can measure where it's going across. You can measure the path. And you can do that from two different spots on Earth, and you can measure that distance fairly accurately. And so with a little geometry, it lets you measure things like the size of the sun, and it lets you work out the geometry of the Earth and Venus and the sun, and figure out the distance of Venus from the sun in like proper units like meters instead of in units of the Earth's orbit. And so that lets you bootstrap. You can get up to the distances for all the other planets. Because now we know what an astronomical unit is. Nowadays, you can do things like radar ranging. You can bounce a signal off of Venus and hear the return signal and do timing to figure out how far away you are, and use that to piece together a more precise measurement of distances to planets. So that's chapter 7. That's going to conclude this video. I'm also going to upload chapter 8 pretty quickly. Chapter 8 is going to be the formation of the solar system. So.